I am Abby J. I'm down the hill at Foothills Lab in MCube. And I in general do a lot of modeling, like regional climate modeling, high resolution modeling, anything. So right now I'm going to be talking about comparing the CESM S2S hindcasts with similar hindcasts using MPAS, the model for prediction across skills, which we developed down at MCubed. And this picture up here is from one of our 60-kilometer initializations. It's just the time I chose, but it's showing IVT, so a measure of atmospheric rivers. And if you squint, you can see like the little polygons from the MPAS grid. But yeah, and I gave this exact same talk at AMS last week. So this is pretty, when I explain things, it's like, I get pretty basic. So I apologize for over explaining. But our motivation here is just that S2S forecasts, as we all know, are very challenging. Our memory from initial conditions are lost, and our skill comes from the interactions with the more slowly evolving systems, such as the land and ocean. In this talk, I'll compare skill from a weather and a climate model, so CESM and MPAS atmosphere. And we're mostly just going to look at surface temperature. I will show one preset plot, but to be honest, I finished these MPAS runs in the last 2 weeks. So this analysis is at a very early stage. So here we will investigate the impact of coupling to an ocean, the impact of horizontal resolution, and we'll look at which model is more skillful. So all the S2S suites that I'm going to show are similar in these ways. So they're initialized each Monday from 1999 to 2022. So in all, we have 1,252 initializations. Each suite has 11 members. They're run out to 46 days. And they all follow the SubX protocol, which apparently I forgot, it has a different name, but it's the same thing. And the lead time dependent bias is removed prior to the verification. And what I'm going to be showing here are biweekly averages of 2-meter temperature for DJF. And the verification data that I verify against is from ERA5 reanalysis. So just to walk through the experiment that I'll be talking about. So this is just our basic CESM S2S hindcast. So it is a fully coupled global climate model, 1 degree resolution. Land model is CLM5. And the atmosphere was initialized using CFSV2 reanalysis, and the 11 ensemble members were initialized using a random field perturbation. So I also did a CAM6 run. It was not coupled to an ocean. The atmosphere is initialized the same way as the previous experiment, and prescribed SSTs are used and come from the OISST dataset. So the MPAS-A experiments, there are 2 different ones. Neither of them are coupled to an ocean. We're looking at 2 horizontal resolutions globally, 60 kilometers and 120. The atmosphere is initialized using the 10-member ERA5 DA ensemble, and the 11th member is just the ERA5 reanalysis. SST is updated daily from ERA5 output for each member, so SSTs are the same across all members. Version 8.3.1 is what we're using. It's basically an out-of-the-box version of MPAS, which I just added a few diagnostics, such as the IVT that I showed earlier. And our land model is NOAA-MP. So the verification metrics that I'll be talking about today are anomaly correlation coefficient, ACC. So high is good, higher is better. Root mean square error, RMSE, lower is better. And then the Murphy mean skill score, with Judith covered in her earlier talk. And high is good for that. And above 0, if it's any amount of red, it means that it's better than climatology. So here I'm just going to compare the fully coupled CESM2 versus CAM6 that was not coupled to an ocean. So in the top row, we have CESM2, middle row is CAM6, and the bottom is CESM2 minus CAM6. And then this bar plot is a global average excluding Antarctica for each of these runs. The blue is CESM2 and the red is CAM6. So CAM6 is performing better in weeks 1 and 2. and CSM performs a little bit better after that. And the main differences that we can see are in the Southern Hemisphere tropics. So these runs are different, but they're not like obviously like a huge deal different. But to compare, and then I'm also going to show RMSE for these runs. So again, it's ESM2 at the top, CAM6 in the middle, and the difference at the bottom. So the red means, on the bottom row, the red means that CAM6 has a lower skill, not lower skill, but a lower error than the ESM2. So CAM6 is doing better here because we want lower is better. And the biggest differences are over the tropics, Northern Hemisphere mid-lats. And these two models are the ones that show the biggest differences in RMSE. There's not as many differences between the MPAS runs. So to compare to MPAS, I mostly want to compare CAM6 because that's like the closest with the uncoupled ocean. So here we're going to look at CAM6 versus MPAS 60 kilometers. This is ACC again. And the top is CAM6, middle is MPAS 60, and the bottom is CAM6 minus MPAS 60. So all those blues means that MPAS 60 kilometer is performing better. The red, the areas in the reds, which unfortunately for weeks 3-4 is North America, means it's doing much worse. So but overall, there are significant improvements shown with MPAS. The largest improvements are over the Southern Hemisphere tropics, and it is summer there for them because this is DJF. And what I find really, really exciting, I think, is that the largest improvements we're seeing with MPAS 60 are at weeks 5 and 6 at the S2S range. So that is exciting to see. So now I'm going to compare MPAS 60 and MPAS 120 to see if MPAS 120, we want to know, is this actually resolution or is it the model? So this is a previous picture I showed you with MPAS 60, and then here's 120, and you can definitely see those polygons a little better, but it's nice to see that everything looks as it should in both runs. And then here's the ACC for both of these, MPAS 60 at the top, MPAS 120 in the middle, and MPAS 60 minus MPAS 120 at the bottom. So higher resolution does have better skills. So all the reds mean that MPAS 60 is doing better, notably over CRONUS and Central Asia, but it's not like significantly better. And I'll show all of these next to ESM and CAM6 next, so we can see that like MPAS is generally doing better across the board. And it's not just the resolution. So here I'm showing for all the models. So at the top, CSM2, then CAM6, third row, MPAS 60, bottom is MPAS 120. So MPAS at 60 kilometers performs best, followed by MPAS at 120. Coupling to the ocean does improve ACC on the S2S range, but not RMSE. And this is just the comparison between CSM2 and CAM6. And then different initialization does play a role for weeks 1 and 2, but less so out to the S2S forecast range. So I do want to acknowledge that yes, CAM6 and the MPAS runs, I'm comparing them. Yes, they were initialized very differently. I am redoing this CAM6 run. I just haven't gotten to it yet, but I'm redoing it, and I'm also going to and I'm also going to update with Verify SSTs so that these are as close as possible. So that is I'm working on getting the input data ready right now as we speak. This talk is actually interrupting my work. But yeah, but what we can see, which is really nice, is the red and the green bars are higher across the board, which is exciting for just like knowing that we can do a little bit better. And then I also want to show the Murphy skill score. So again, the rows are the same, but what we can see, and Judith mentioned this earlier, is that with MPAS and also with CAM6, something's happening when we're turning that ocean off. And we're getting like better performance with this Murphy skill score. And I really don't understand why. So like CAM6 is improving, like especially in over the rainforest in South America and in Africa, like, and even in like up in northern Russia, Siberia. there's something going on there that we need to like kind of figure out what's going on. And then MPAS is also performing better than the CAM6. But if I do this global average thing again excluding Antarctica, we can see that out to weeks 5, 6, the only model that on average is doing a little better than climatology is MPAS 60. And that's like a tiny, tiny, tiny bit. So we have, like, according to this skill score, which I don't super quite understand, this is like, I've only been using it for like a month or two. But there's like more research that needs to happen to see what's kind of going on, especially in the tropics. And then I will show one precipitation plot for ACC. And again, these are all 4 runs. Really hard to see any differences just looking at it like this. But if I do like the local average, we can see that on average MPAS 60 continues to perform the best, even if only slightly out in weeks 5 and 6. I think looking at precip can be like a lot more interesting, looking more regionally and maybe on state dependent work. So in conclusion, these S2S forecasts were evaluated using the 3 different models, CSM2, CAM6, and MPAS at 2 different resolutions. For both 2-meter temperature and precipitation, MPAS was better than CSM at resolutions, especially in the tropics. And then the mean skill in the extratropics is typically not better than the climatological forecast, as shown on the Murphy skill score. But when we condition on the large scale state at initial time, skill is regionally better than climatology, i.e. with ENSO and PNA. And this is some like early work that we've started with these runs. And future work, we do want to look more at state dependence. We want to see if the predictability horizon is estimated by a perfect model is met, similar to the work Judith just showed. And then I did mention this, we're going to rerun CAM6 with the same initial conditions as were used for MPAS, the Aero Ensemble. And then we're also going to run a subset of these hindcasts over, I think, a decade and summers over 2 regionally refined meshes using MPAS. So one will be a 60-kilometer global down to 15 kilometers centered over CONUS. So it's an area that's 55 latitude by 110 longitude. And then we're also going to do one that's 64-kilometer global to 4 kilometers over central CONUS. And that refined area is 16 by 16 latitude and longitude. And these are like some maps just to see, but yeah. And then here's a few references that we're working on, Judith and I. And then any questions?
I think by default, the AMIP comp set doesn't have the geochemistry on in the land.
Okay.
It depends which one you use, but my guess is that could be the reason for the big differences.
Okay.
As opposed to ocean, not having a coupled ocean. It might be good to.
Okay. Judith, do you know? No.
As you could either use the FHIST_BGC or FHIST. And I think if you used FHIST, it's with satellite phenology, whereas the coupled ones would have biogeochemistry.
Okay. I believe it was FHIST, but
I think so too, yeah.
yeah.
Sorry, which one? The
FHIST, yeah.
Yeah.
I feel like that's more likely.
Is that over the tropics?
David, no, but yeah, everywhere, yeah. But
Just means your vegetation state is probably not big percent prescribed.
they probably have the big impact in these rainforest regions.
Yeah. Okay.
Be biased in a couple of models.
Yeah.
Or biased because of the precipitation biases. So.
I'm curious if you can rerun the CAM6 using NOAA MP land. Is that an option? I mean, because that's a major difference between these.
Right. That is. I don't know enough about CAM6. Is it possible?
Hello, CIMA. Right, I mean, I think under CIMA and CCPP, we should be able to do it. But currently, I don't think there's a concept.
I feel like you could run MPAS with CLM, right?
It's the other way around. I don't think that no MP is in the CSM thing. Right?
Yeah.
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 That would be a good way.
Good point.
See what's
And I
going on
mean,
now.
some of this is, I mean, this work is partly funded by ASPAT, right? The land atmosphere interactions. And that would be super interesting to do, especially because of this big discrepancy in the
I mean, even with a lot of the testing I was doing, a lot of my testing to get these MPAS runs going was like playing around with options in NOAA MP, because it's still, honestly, it's still like very early in its MPAS life as well. And like, this is kind of the first big project that it's been used on. So
Was it spun up the same way that CLM was spun up using atmospheric reanalysis?
yes. For like, I think it was like a 30-year run.
One more question.
Comment and question. Comment, and this goes to this, for yours too. Compare to IFS. You should, when you, especially when you're talking about this model is better than this one, you'll see what better looks like, and then you'll have a better idea of what.
Yeah, we have been comparing that.
Okay, good.
I was mostly focusing on this for AMS with the two NCAR models.
Yeah,
Push NCAR real good.
but it's good to,
Yeah.
yeah, it's good to see where you are.
Yeah.
Also, now, this was year-round skill?
What I'm showing is DJF.
You just showed.
Yeah.
Have you looked at it in the season?
Yes.
Do you
Like-
see the same sort of picture?
Yeah, the same patterns are there.
I mean, it's also, you looked at precip, you'll notice that, yeah, I mean, I think again, this is this trend issue in temperature. So I think you need to worry about that when you look at, when you're scoring it, the precip is a thing.
Yeah.
People ultimately care about, so.
Yeah, I've also been looking at like Z500 and PSL, SLP, to look at how they're performing against each other as well.
We should move on. Next is Gary.
Even though the other speakers have been seated, I'm back here in the sun, so I may go up. I'm not a Google person, but right. I don't know if we can maximize it any more than that.
Put it in full screen mode.
Is that
Full screen mode.
Let's came up
You,
with
this
that.
happened earlier, I think, had to share the full screen
oh,
as
yeah.
opposed to the.
Yeah, if you share your full screen.
Sometimes here.
Yeah, I feel like Abby's results are kind of maybe telling us the answer for why we have degraded skill. Right? If you don't have the BGC on and it doesn't have that negative skill.
Hang on, so-
I didn't think of BGC. We know we super under dispersive in the tropics in CSM. This was where my mind was going, but you know, I'm open if BGC is fixing it, you know, because
Yeah, and then just-
it's so poor in the tropics on the S2S timescale, so it would be on longer timescales too. Yeah, I think it's a super interesting.
Yeah, okay.
Yeah.
Have you looked, I mean, have you, with the MJO and what your skill looks like?
Just decent in that model.
Sent to find how,
I
Okay,
didn't
wait,
see
here.
some great.
skills, real skills.
So this is some preliminary results of kind of exploration we've been doing, kind of see what the effects of soil moisture initialization could be. Motivation for this was actually a paper that was published in 2024 by Peng-King Chi, Ruby Lung, and other co-authors who claimed skill in predicting the 2003 European heat wave 2 years in advance. And they claimed that they got that skill from initializing soil moisture for the Tibetan Plateau, which somehow persisted for 2 years and then drove a teleconnection pattern that affected the European heat wave. So we said, well, let's look in our hindcast and SMILE hindcast to see if we see any of that. And it turns out we didn't see anything 2 years in advance coming from the Tibetan Plateau, but we did see something coming for a year in advance from the Western US. And that's kind of where we end up going with this. And the reason we think that we could get maybe some skill coming out of soil moisture conditions over the US that could affect European heat goes back to some work that Haiyan Tang did when she was here 2019, where she was looking at the effects of the Dust Bowl drought. She was putting in these really dry soil moisture anomalies in the model over North America and she saw this wave 5 teleconnection pattern. This wave 5 teleconnection pattern is an interesting teleconnection pattern because it's a summertime pattern. It's not driven from the tropics. It seems to be driven by land surface anomalies in the Northern Hemisphere. In this case, you can see that she put in an idealized lower tropospheric heating over that box over the Great Plains there. Heating profiles on the right, that red line shows the really strong heating, kind of 850 hectopascals. And you see this kind of wave 5 teleconnection pattern with one of the high centers kind of impinging on Europe there. But this wave 5 pattern shows up kind of in a lot of different applications, and it's never quite the same. Depends on where the heating is put in and how the pattern sets up, but it does have this characteristic kind of wave 5 set of features. So it's kind of intriguing. It's maybe a way to connect North American soil moisture anomalies to what's going on over Europe. And then we followed that paper up with looking at heat extremes on the decadal time scale over the Dust Bowl drought years in the 30s. And this is the upper left plot there is looking at what we call the records ratio. It's a ratio of daily record high maximum temperatures compared to daily record low minimum temperatures. When the ratio is above 1, that means you're getting more record highs and record lows. In other words, you're getting more extreme heat. And of course, over North America, or over the US there in the upper left, the 30s stand out. That's very well known. It was really hot and dry over the US during that time period, only to be kind of exceeded very recently in the 2020s. But if you look at areas over Europe, Sweden in the upper right there shows a big bout of extreme heat in the 30s. Lower left, Germany also stands out in the 30s, and even Russia has a little bit of a peak there in the 30s. So it looks like there is a connection between North American soil moisture conditions and European extreme heat. But this is on decadal timescales, right? This is looking at a decade of the 30s. And the question is, could these soil moisture conditions have predictive value on interannual timescales? So that's what we're going to be looking at here. So motivated by the fact that the Xi et al. Paper was looking at the 2000 European heat wave, we're going to see if we can what we can see about that. The preconditions for this were over North America, over the Western US, there was a big drought in 2002, as it turned out. It was an exceptional drought, and it was very notable. And then that drought persisted into 2003, and it was still dry in the Western US in 2003. And of course, summer 2003 is when the big heat wave and drought hit in Europe. It's a really kind of a striking kind of thing with a lot of fatalities, and of course, a big drought and big heat extremes. So what we're going to do is do a case study to explore these possible predictive value of the US soil moisture anomaly. So we're going to look at the SMILE simulation initialized in May 2002. Run it forward. We're going to look at 13-month leads for June, July, August 2003, 20 ensemble members. The initialization parts of this, the oceans, the standard FOSSI. The soil moisture initialization deserves a little bit more description because that's key to this whole thing. The way that this is done is you take the land model, run it offline with observed atmospheric forcing, put those conditions back in, and those are the soil initial states for the hindcasts. We're looking at some observed soil moisture anomalies. This is the ESA CCI satellite-derived product. Observed SSTs are HADIST, and ERA5 for the rest. Okay, so upper left is the initial state soil moisture anomalies in the model for May 2002. And you can see the oval layer over the Western US. We're capturing this drought that was occurring, depicted in the drought monitor map there on the right. It was a pretty big drought in 2002 in the Western US, and those red colors there in the upper left over the US are capturing those conditions in the initial state. To compare those initial state anomalies to the observed soil moisture anomalies in May 2002, you can see that the observations also show dry conditions, probably more extensive than what the model initial state shows, but we're still getting that drought in the Western US. And when you look at Europe, in both the model and the observations, not much going on. So the action in May of 2002, summer 2002 is basically over the Western US. Now let's look at the 13-month lead predicted soil moisture. And as we noted, the drought in the western U.S. persisted, and the prediction picks up on that. You see in that lower left panel there, the oval over the western U.S., the red colors indicate continued depleted soil moisture. But now when you look at the oval over Europe, now you see those red colors, and that's the drought over Europe that's being predicted by the model in this hindcast. So the surface temperature anomalies is what they look like. Of course, in the upper left there, these are the predicted surface temperature anomalies from the model, and you can see it's red over the western U.S. and darker red over Europe. And compared to the observations in the upper right, it's a little bit bigger magnitude positive anomalies, surface temperature anomalies over the western U.S. In the observations, but still present in the model. And of course, even darker red colors for Europe compared to the observations. But we are getting, or compared to the model, we are getting some evidence of elevated heat in the prediction. Lower left is the predicted soil moisture anomalies. Again, that's that same map I just showed. The observed soil moisture anomalies for June, July, August 2003 also show continued dry conditions over the western U.S. There, and dry conditions over Europe, those red colors over Europe. So it looks like the model is getting at least some elements of this heat and drought predicted 13 months in advance over Europe. If you zoom in to see regionally how the model is doing, the model surface temperature anomalies on the left, observed on the right for June, July, August 2003. You see it's not quite in the same place in the model. The heat is more in Spain and southern France. In the observations, it was more in central France, extending up into Germany and other parts of Western Europe. But we are getting elevated heat in some areas of Europe, which to me was amazing. I didn't think we were going to get anything out of this, but we are getting something that kind of looks, at least qualitatively, like what we saw in the observations. So how do we think we can connect what's going on over North America to Europe? And we have to go back to this wave 5 teleconnection pattern. The upper left is the 200 hectopascal height anomalies for June, July, August 2003 coming out of the model. And you see that wave 5, pretty nice wave 5 teleconnection pattern with a high over Western US and a big high over Europe as part of that wave 5 pattern. Very close to the observations, actually. The observations also see on the right that anomalous high over the Western US and an even stronger high over Europe. So it looks like the model is getting something that we actually observed. And we again reference back to this idea that these lower tropospheric heating anomalies over the US could actually possibly produce this wave 5 teleconnection pattern. This is a little bit differently configured version of High-End's figure. But again, showing that at least for the central US, you can excite this wave 5 pattern that connects over to parts of Europe. And of course, the heating is not quite in the same place in the model because it's more Western US, not central US. I think the general idea is that it looks like the model is picking up on this connection that can, the soil moisture anomalies over the US can affect what's going on over Europe. Okay, to summarize, the previous work demonstrated that very dry soils and heat extremes over the US during the Dust Bowl in the 30s on decadal timescales can be connected by a circumglobal wave 5 summer teleconnection pattern heat extremes in Europe on decadal timescales. And the question we asked, could this connection also exist on interannual timescales to give us predictive value from US soil moisture conditions, the drought in 2002 and the subsequent European drought and heat wave a year later. We did initialize hindcast case study with the SMILE hindcast to see if we could get any aspect of predicting 2003 European heat and drought. We saw that the initialized negative soil moisture anomalies in the Western US, they weren't too bad compared to observations. And that was another kind of surprise. We didn't really know how this initialization we were using, where we're forcing the land model offline and putting it into the model, how those actually compared to observations. And at least for this case, they look pretty good. The initialized anomalies over the Western US are negative in May 2002. But there's nothing really going on over Europe in either the observations or the model in May 2002. And then the initialized 13-month lead prediction for summer 2003 shows that these soil moisture anomalies persisted over Western North America. And that contributed to this wave 5 teleconnection pattern that seemed to contribute or produce this anomalous high over Europe and anomalous heat and drought over Europe for the June, July, August season of 2003. Thanks.
So Yeah, so super interesting. Do you have a sense on like how strong the soil moisture anomalies need to be to kick off that
Oh,
zonal wave?
That's a
number five?
question, yeah, that's a good question.
All right, let's do it.
Yeah, yeah. We gotta resurrect the specified heating anomaly version of CAM. I don't know if that still exists or not.
I mean, can I follow up to, do you know, like if do you think the soil moisture anomalies are the sole contributor to the zonal wave number 5?
It's hard to
Because
say.
yeah, I mean, I would think there might be some
It
sort of.
seems to me like in Peng Fei and Ruby's paper, where they're getting this 2-year lead, it looked to me like it was a chain reaction, like the Tibetan plateaus may be affecting the US, that would then affect Europe over a 2-year period. But that paper's kind of funky, and I still don't understand exactly what they did, but
Ruby has a question for you.
Ruby's on Ruby.
Yes, yes, yeah. Can I?
Yeah, please explain it.
Well, I'm not going to explain my paper, but I'm just trying to say, first of all, really nice analysis. I really enjoy your presentation. And secondly, what I wanted to say is that I don't think your results necessarily contradict our results, because essentially you can also ask like what created that soil moisture anomaly in May of 2002 to begin with, right? So
Right.
Potentially that anomaly could come from some other type of anomaly that existed earlier or something like that. So in our paper, we were trying to make that connection to say that the Tibetan Plateau snow cover could induce anomalies over the North Pacific Ocean. And so it is partly the connection from the land to the ocean, which then have some kind of persistence that potentially create these subsequent anomalies, right? So I think, I mean, given your analysis, I think we could also go back to our simulations to do more analysis of how potentially connections between Tibetan Plateau to the ocean to the Western US soil moisture anomaly in May 2002, which then subsequently set up the mechanism that you talk about. Yeah, but all I wanted to say is that it's not contradiction, because essentially you can ask like what set up that May 2002 soil moisture anomalies to begin with.
Yeah, and I think that when I was saying I couldn't understand, it's that linkage you just described, I didn't really understand in the paper, but I think, and I did take away that there's a chain reaction effect, right? So there's something,
Yep.
plateau affects something downstream, which then affects something over Europe. So it's that chain of that connection chain that I think is interesting.
Great, thank you. Yeah.
Okay, thanks, Jerry. I think we have to move on to try to get back on time. And our next speaker is remote, Gwyneth Blanton from, I believe, University of Oklahoma. Gwyneth, are you on?
I am. Can you hear me?
Jerry, could you stop sharing?
Yeah.
Okay. Can everyone hear me?
Yep, it looks good.
Awesome. Hello, everyone. I'm Gwyneth Glanton. I am from the University of Oklahoma. I was recently in Boulder, so I met a few of you guys while there, which makes this a little less intimidating. But I had to get back to Oklahoma to do some things. So I really appreciate being there. But I also presented this at AMS, so it is a little bit of a watered down version. And I also did not use the fancy template that I see a lot of you guys did use. But today I will be showing how I assess the skill and reliability of the NCAR CSM SMILE to help with the predictions of the North Atlantic subtropical high in multi-year timescales. So to go over, most of you guys already know this, but what is the North Atlantic subtropical high, or NASH? This is a semi-permanent high pressure system located over the North Atlantic, and its strength and position vary, with the most notable changes occurring in the Western Ridge, which is primarily what I'll be focusing on today. So how do we define this Western Ridge? We looked at where the easterly components, which is an example, or easterly components of the wind reverses to the westerly components of the wind, or that zero wind line, which is an example on the plot of the left shown with that blue line overlaid on the average wind speed. Intersects with the average geopotential height 1560 GPM isopleth, and we found the most western ridge point to define those western ridges. And I got, this is an example from one for all ensembles for 2019 for that SMILE data set for a Western Ridge. And then from there, I calculated climatology and was able to define the Western Ridge into 4 different quadrants, the northwest, northeast, southwest, and southeast quadrants. And this is an example from ARA5. But that's just some of how we define those things. But my motivation for this and sort of what is influencing that Western Ridge is the variability of SSTs can impact the NASH through specifically the AMO. And when the AMO is in cold phase, the NASH is stronger and shifts northwestward. And when the AMO is in warm phase, the NASH contracts and shifts northeastward. So we think that that could be an impact. And in recent decades, we have found that the NASH Western Ridge has shifted more westward. And if that low frequency variability of SSTs is the cause of this shift, then we need initialized predictions to break the shift. Then that's where the SMILE data set comes in. These shifts can affect extreme heat, precipitation, drought, and coastal undulation, particularly during the summer in the United States. So that's what I decided to focus on, and specifically in the Southeast US. So intervariability of the summer precipitation in the Southeast US has increased significantly in recent decades, and this poses threats to a region's water supplies by altering runoff, increasing soil erosion, and affecting crop yields, which can have a major economic and socio impact on a region. But to get into what main questions I tried to answer is, how will the NCAR CSM SMILE model correctly predict the variability of the NASH, and how is that shift in the NASH impacting precipitation variability, particularly in the Southeast US? And how did the model do with predicting this? So the data sets I used the SMILE data set, which is, if you recall from, I believe, Tuesday on the updates, Stephen went into detail about what this model entailed, which is 1 month to 2 year runs, initialized quarterly from 1970 to 2019, with 24-month runs containing 20-member ensembles. And I like that it's SMILE, which, if you know me, I'm a very smiley person, so it's kind of funny that I'm using this data set. And then I also compared this to ARA5. I treated ARA5 as truth, and CHIRPS for our precip, which are 35-year quasi-global rainfall data sets ranging from 1981 to near present. So to get into that first question of essentially the skill of the SMILE data set and how it did, I wanted to just do an eye test of how similar the model was to the reanalysis data, which just by eye, you can see that this is the composite height anomalies with GPM lines overlaid in black. On the left, we have ARA5, and on the right, we have the quote unquote first summer of the SMILE, which is the I divide summer by June, July, August. And so this is for the first initialization across all 50 years and 20 ensembles, which would be leads 3, 4, and 5 for that first summer. And it's also separated by quadrants: northwest, northeast, southwest, and southeast. And just by eye, you can see that it does a pretty decent job. There's some minor differences, but the general patterns are there with some strength varying. But then I wanted to really look into how quantitatively there was a difference. So I took the difference plot in ARA5 and the data set, Western Ridge location, and then lead time is here on the x-axis, which is showing months since the initialization. And the box plot and scatter points show the ensemble range of error across all 20 ensembles in years. And just from first glance, you can see there's north-south on the top and east-west on the bottom. And north-south has a smaller difference in error than east-west. You can see this from the y-axis, with north-south being ranging from -20 to 20 and east-west ranging from -80 to 100. So there's a lot more variability in the error in the east-west. And to get a little closer look in that difference error, we can see that for the error, that there are similar errors amongst link times, which is indicating a potential seasonal difference rather than, I guess, like a lead time dependence. And so if you look at the third lead time, which is June, compared to the 15th lead time, a later lead time in June, the error seems to be very similar. And I wanted to look into that a little bit closer to see if it was lead time dependent or seasonal dependent. So again, I went back to the composite height anomalies for first summer and compared that to the second summer, which would be leads 15, 16, and 17. And again, with that eye test, you could see that farther lead times produce similar results to closer lead times for corresponding months. And very, very similar. And this seems to also hold up when looking at that error plot. So then I wanted to see if across initializations, this was the same case. So I compared all of the initializations for this. I'll just look at 2 of them. And yeah, that numbers of error for error 5 compared to the data set again hold up for the same months, corresponding months with each initialization, which indicates that there is less error in the NASH position for some seasons versus other seasons, particularly fall and summer, which I wanted to dive into further and sort of provide some motivation of why we focused more on the summer as well. So it seems that the model was better at predicting the Nash Western Ridge position for the summer compared to the fall. And if we just take a look at this, I have this plot to the right, which shows the quarterly initializations, if the model correctly predicted the quadrant of the Nash Western Ridge across all years and ensembles. So looking at this, November, not too hot, less than random across all initializations, around 20% of correct predictions. But if we look at, say, summer, we do a lot better with our predictions in the right or the correct quadrant being around 35%, which is better than random. So if these summers are predicted correctly more frequently, this leads us to circle back to that quadrant question and ask if there's a certain quadrant within the summer period that's being better predicted for the models. So this is a plot for all 4 initializations and going back to the quadrants. So each plot shows quadrant data and the different initializations with each quadrant and how accurate those predictions are. So it seems that the northwest quadrant and the southeast quadrant are doing pretty good. And if we recall the AMO and cold phase, the Nash strengthens to the northwest, which I found interesting because going back to our plot before, the Nash seemed to be better predicted by the model in seasons when the Nash was less variable, because in the summer, the Nash is a little bit better location-wise, but in the fall and winter, the Western Ridge location is more variable. And so it makes sense because in that cold phase, when the Nash is strong and shifted, the northwest would be better predicted. But why the southeast is better predicted, I'm not quite sure. And that's a little bit more confusing to me. But when the Nash moves north, particularly northwest, it's associated with higher than normal temperatures and a lack of precipitation. And when it's southwest, it's associated with particularly higher precipitation, and when it's shifted to the south in general, which leads me to my next question of how is that shift in the Nash impacting precipitation variable, and how is our data set doing with predicting this? I didn't get too far into this question before AMS, so I only have one plot to sort of look at, but this shows for the second initialization, which is closest to summer, which is the May or June, initialization, and this is the first summer, so it's those really close lead times across all years 1981 to 2019 and all ensembles. So this plot shows the correct quantile prediction of dry, normal, and wet, which dry is less than 33rd percentile and wet is greater than 66th percentile, and the correct quadrate prediction. So this is only showing data for both of those correct. And if we take a zoom and to look at this further, the color bar is showing how frequent the correct percentile appears within the correct quadrants. And it can tell us, so basically what quadrant is better. That's predicting what quantile and where this is occurring in the Southeast US, which will be really helpful later down in the line. And if you call the model was better at predicting the Northwest and Southeast quadrants, better than other quadrants. And the Northwest quadrant seems to be predicting dry conditions pretty well, especially in those in the Florida region. And then the Southeast quadrant seems to be better predicting wet conditions, which I thought was a good sign since the Southwest shift is associated with more precip and the Northwest shift is, or a northward shift is associated with less precip. But I'm still kind of working on this and trying to find my direction and where this is going. So basically, the model resembles the reanalysis data more closely in the north-south direction. There seems to be a seasonal correlation of the error, and the model better predicts the Nash position during summer and in the northwest and southeast quadrants. And then getting into precip in the southeast quadrant, the model is better at predicting wet conditions. In the northwest quadrant, the model is better at predicting dry conditions. So what does this mean for the Nash's influence on precipitation variability, and how will this data set of the model predict these influences is later down the line. And if you have any suggestions, I encourage it. So, yeah.
Maybe one question. Jerry.
Yeah, I mean, this is really interesting, and the Nash is always very intriguing just for the U.S. precipitation connection, but I was curious if you had any idea of what moves it around. I mean, what conditions make it move one direction or another?
Yeah, so that was another part of this project that I started to get into, and then we decided to take sort of the precipitation route, but we think that, and why we're using the SMILE data set is because of SSTs, and that SSTs could be that driver of the variability in SSTs. So I started to look into that a little bit with some anomalies, but I didn't get as far deep into that. And that'll be another part of this project that I think another member of my group will work on.
Great, thanks.
Thanks a lot, Gwyneth. If you could stop sharing, we'll move to our next speaker, Yiming Guo, another remote presentation.
Can you see my screen right now?
Yeah, but not full screen.
How about now?
Good.
Okay. Oh, sorry, let's do that again. Okay, sorry about that. Yeah, hi everyone. My name is Yiming Guo from Illinois State University, and today I will be talking about does dynamic downscaling can improve multi-year prediction skill on the Northeast continental shelf of the United States. So this region is ecologically and economically important, but predicting its variability like beyond seasonal scales remains challenging. So in this work, I will show how regional ocean downscaling compares with global climate predictions and where it adds value. So why the multi-year prediction matters in this region? So over the last decades, the Northeast Shelf has warmed faster than any other marine ecosystem in the country. So this rapid warming has already driven major shifts in the distribution of fish stocks and protected species, which creates a growing challenge for fisheries and ecosystem management. And at the same time, predicting the conditions on the shelf is difficult because global climate models are just too coarse to resolve bathymetry and key shelf processes. So earlier studies suggest that large-scale climate predictability exists in the North Atlantic, which includes skillful tidal prediction. So this motivates the central question of this work. Can dynamic downscaling translate large-scale predictability into useful multi-year forecasts on the shelf? So therefore, we plan to do a dynamic downscaling of CESM Decadal Prediction Large Ensemble, DPLE, using a regional ocean model system, ROMS. So CESM DPLE is a 1-degree model, and it has over 60 initialization days and 40 ensemble members. So besides CESM DPLE, we also use GLORIS reanalysis. So GLORIS is a global 12th degree ocean product. But where does GLORIS come in this framework is that when we force the regional ocean model, we only use the anomaly fields from DPLE to reduce the impact of mean bias on the regional system. Instead, the climatological fields are from ERA5 in the atmosphere and GLORIS in the ocean. So this anomaly downscaling approach allows the regional model to evolve around a more realistic mean state while inheriting large-scale predictability from CESM. But due to the available high-resolution atmospheric output from DPLE we can get, we only chose 20 start years and 10 ensemble members for the experiment design. Each simulation runs for about 8 years. And here is a little bit more information about the ROMS downscaling. So it's a high-resolution regional ocean model, which operates at about 5-kilometer resolution and is forced using anomalies from DPLE. And the model includes tides, rivers, and realistic bathymetry. And as I just mentioned, we perform 8-year prediction for 20 initialization days with 10 ensemble members. So this kind of gives us a framework for assessing the multi-year predictability. And before running the downscaling simulations, we also developed a hindcast simulation using ROMS. So ROMS hindcast here is a standalone high-resolution ocean simulation. It uses the exact same configuration as the downscaling system, but just forced by ERA5 and GLORIS directly. So this hindcast is kind of a baseline for the performance of this regional system. And this plot is the model domain we use, even though it's a larger model domain in terms of a regional model, but our analysis mainly focused on the shelf region, which is bounded by these red lines. And this small region consists of 3 ecosystem provinces, Gulf of Maine here, Georges Bank, and the third is Mid-Atlantic Bight. So to start, we first evaluate how well the regional and global systems reproduce the mean structure of some key ocean variables on the shelf. So here we compare the time and ensemble mean conditions for surface variables like temperature, sea surface height, and sea surface salinity across different data sets. So the ROMS downscaling is this column, and the last column is from CESM DPLE. So you can see across all variables, CSM exhibits like a mean state biases on the shelf. For example, the SST is too warm and SSS is too salty. And this is kind of a well-known issue in the low-res climate model that the Gulf Stream separates too far north near Cape Hatteras, which largely weakens the cross-shelf gradient. But the ROMS downscaling captures a much sharper shelf slope gradient and a more realistic Gulf Stream path, which substantially reduces the mean state bias. And these improvements extend below the surface. So here we further examine the upper ocean heat content, the first row, and the bottom temperature, the second row. So in depth, ROMS downscaling preserves the shelf properties very well compared to GLORIS. But CSM DPLE still lacks a realistic shelf structure in bottom temperature and heat content due to coarse bathymetry and simplified coastlines. So next, we would like to look at the prediction skill in the two prediction systems. Here we assess SST prediction skill using the anomaly correlation coefficient, ACC. So the first row is from RAMS downscaling, and the second row is CSM DPLE as a function of lead time, from lead year 1 all the way to lead year 8. So we observed a couple of things here. First, the downscaling does improve the prediction skill of SST, especially at this shorter lead years. And second, the CSM DPLE is actually not doing a bad job at all. So their skills are high too, especially for like lead year 6 and lead year 7. So the improvement also varies a little bit differently if we look at different marine ecosystem provinces. But we want to understand why RAMS downscaling improves prediction skill, or where does the source of the predictability come from? So we further decompose the ACC of temperature into 3 contributions, one from linear trend, the top row, and the low frequency contribution, the middle row, and the contribution from high frequency variability on time scales shorter than 10 years, the third row. So I'm only showing the RAMS downscaling decomposition here. But this decomposition shows that a large fraction of the total prediction skill is attributable to the linear trend. So this indicates that much of the correlation skill arises from the externally forced swarming signal, which also explains why CSM DPLE also performs well at this some of these lead years in SST. But we also notice at shorter lead times, like lead year 1, 2, or 3, the interannual to decadal variability also contributes to SST skill. And this is where regional downscaling adds value by better resolving internal variability driven by shelf processes that are not very well represented in the coarse global model. So if we look at a different variable, here is sea surface salinity. So the story is a little bit different. So it's still the ACC of SSS decomposition from RAMS downscaling. So unlike SST, where the warming contributes the most to the prediction skill, the skill in salinity mostly comes from the high frequency variability, which is the last row. So this band is actually not very well simulated in the global model. That's why if we compare the ACC skill improvements, which is measured by the difference of ACC between RAMS downscaling and CSM DPLE, the SSS improves a bit more compared to SST across all subregions on the shelf, and especially at shorter lead times. So these are SST and SSS. If you look at the subsurface variables, we can also see the improvements still exist in the downscaling system. And in addition to ACC, which only quantify the phase of anomaly, we also calculate the mean square skill score to know more about the amplitude improvements. Again, the improvement exists across all the 4 variables we focus here. And besides these deterministic metrics, we also look at Brier score. So Brier score basically assesses the prediction probability errors. So a lower Brier score indicates a higher forecast reliability and resolution. So if the difference is negative, that means RAMS downscaling improves the prediction of these extreme events better than the CSM DPLE. So the bottom line here is the dynamic downscaling improves both deterministic and probabilistic prediction skill by better representing the interannual to decadal variability and extreme events on the shelf. But if the predictability mostly from the trend, the improvement is less. So we have shown the improvements in downscaling. So we next wonder if we can use this set of simulations to look at the prediction about some regional processes. Like here is one example about slope water mixing in the Gulf of Man. So this is Gulf of Man and this is Georges Bank. So the slope water mixture can translate basin scale signals into shelf condition that can have direct ecological and management importance. So here is a channel called Northeast Channel in this red box. So this is one of the most important pathway for mixing of distinct slope water masses entering into Gulf of Aman. So to examine slope water mixing through this channel into the Gulf, we adopt a method following Mountain 2012 and describe the system using the 3 end members, warm slope water, Scotian shelf water, and Labrador slope water on the temperature and salinity diagram. So these are the annual mean and ensemble mean data points. So you can see the magenta is from DPLE, blue is Glorious, and cyan is for RUMS downscaling. So CSM DPLE overall exhibits a warm and overly saline bias, but RUMS downscaling shows a more realistic simulation of intermediate and deep water mass variability in the Gulf of Aman compared to Glorious. So this allows us to further examine whether the mixing ratio from different water mass is predictable or not. So we calculated the prediction scale for the percentage of Labrador seawater, and this is a preliminary result. It suggests that it seems that there is a high prediction scale. So that makes sense to some extent because the variability in the slope water mixture is influenced by both the large-scale circulation changes, such as NAO-related variability, but also intrinsic ocean dynamics, including like offshore Gulf Stream meandering and eddy intrusions. But this result may shed some light on the predictability of some of the key shelf processes, such as Gulf of Aman mixing ratio. Okay, so this is my last slide. So basically, we compare the dynamic downscaling with the CSM DPLE, and we see an improved multi-year predictability. And also, the source of predictability differ among different variables, and there can be different contributions. And regarding regional processes, the downscaling also improves representation of a couple of processes we focus on, like slope water mixing in the Gulf of Aman or the cold pool dynamics in Mid-Atlantic Bight. But also, while dynamic downscaling improves realism and regional predictability, it does not eliminate fundamental limit sets by internal variability, sampling, and also model biases. But it also opens to future opportunities, like we can use larger ensembles, longer hint cuts, and improved circulation physics that resolve some mesoscale dynamics, or even using a coupled regional prediction system, which may enhance multi-year prediction scale on the shelf further. Okay, I think I'm gonna stop here and leave the summary page here if you have any questions.
Maybe time for one, Matt.
I don't know if you've gotten a chance to compare this to the Ross et al. Work, which did something similar with Spear. My impression from theirs was that mostly the downscaling was proving the estimate of the trend in the model, because there's an erroneous predicted trend in the model, pretty bad actually in that region, which the downscaling actually improved. I never really understood why. And I was curious if that was, if you're seeing anything similar. If you were to entirely remove the observed trend from your verification and the predicted trend from the model, have you done that first? And if you haven't, do you have any sense of what you might get?
Yeah, just yeah, I should double check what Rose et al. Concluded, but we did try to remove trend and recalculate the scale. But just regarding SST, that's true. Most of the predictability scale gets reduced after removing the trend. But for the other variables like surface salinity, removing the trend is not changing the overall scale very much.
Okay, thanks a lot, Yiming. Great talk. We'll move on to the final talk before break from Dylan Oldenburg.
Hi. Okay, let me share my screen. Okay, 1 second here. Okay, can you see?
Yep.
Okay, great. Hi, so I'm going to be talking here about the subpolar North Atlantic upocean heat content predictability in all of the available CMIP-6 decadal prediction systems. So what drives this predictability? And so the goals of this work are to determine, firstly, to determine the subpolar North Atlantic upocean heat content predictive scale in all available CMIP-6 decadal prediction systems. And so here use low and high skill models. So all available models, we want to understand why some models have higher skill in this upocean heat content, and other ones have lower skill. And the question here is, so in all of these models, regardless of skill, do we have the same linkages between the Labrador seawater deeper ocean density and the later AMOC and the changes in subpolar North Atlantic upocean heat content, or are there big discrepancies where some models aren't showing these clear linkages? And if so, then why is there this lack of skill in some models? Is it driven just by incorrect variability at the initial times in these hindcast simulations? And so for this work, we use the decadal prediction hindcast simulations from CMIP-6. These are 10-year simulations with the exception of EC03CC. And these are all initialized from different reanalyses and observations. And a main part of this will be computing the lead regressions between the initial Labrador seawater density, the interior density, so between 1,000 meters and 2,500 meters, and then the subsequent upocean heat content changes in the subpolar North Atlantic, the sea surface height, the AMOC, and then the subpolar gyre via the barotropic stream function, and the Labrador seawater thickness. So the models here show a wide range of North Atlantic upocean heat content skill. So this shows the predictive skill of the subpolar North Atlantic upocean heat content in these various prediction systems. And this is the anomaly correlation coefficient computed relative to EN4 for the latter half of these 10-year simulations. So years 6 through 10 after the time of initialization. So we can see here our very high skill models are the CESM simulations, CESM1, CESM2, and then CMCC and HADGEM3. And then we have more of our mid-skill models with MPE, Max Planck Institute, and then ESA-Earth 3 and Meroc 6. And then our lowest skill models here are BCC, CAN ESM5, and FGOLS. And so we can also, it's also nice to view this relative to the multimodal mean skill. So we can see here that really highlights the high skill of the CESM models and CMCC and HADGEM3. We're not really going to focus much here on CESM1 because it's been studied in great detail. And we can see here that this box highlighted here is really the area with the largest standard deviation in the skill. And so it's interesting to look at the time of initialization, to look at what these models are doing, like at the time of initialization in subpolar North Atlantic upocean, in their subpolar North Atlantic upocean heat contents. So here, this just shows high skill models, excluding CESM1, which looks fairly similar to CESM2. And they're pretty well correlated with one another, and they're decently well correlated with EN4, but the climatologies are somewhat off. And for the low skill models, the climatologies aren't really any farther off than for the high skill models. So other models in between that we're not really talking about here because of limited time show much larger discrepancies. Some models are just way too warm in the North Atlantic and others are too cold. And these are less well correlated with one another and less well correlated with EN4. And these models show pretty large drifts in their climatologies. So these are the lead dependent drifts in these simulations. So CESM2 even, which is really our highest skill model here that we're showing here, has a pretty large drift. So this is not indicative of the skill at later years in the simulations. And we can also look at just the anomalies. So that will just indicate how good the variability looks at month 1, how aligned they are with EN4. I mean, the difference here is that all of these simulations, a lot of them are branched from different reanalyses or observational data sets. So some of them are branched from something very similar to EN4, and then some are branched from various other reanalyses, like AURA, for example. As we can see, the high skill models are very in line with each other and pretty well in line with EN4, and the low skill models are not as well aligned. And so since we're interested in understanding the mechanism driving this uprush heat content predictive skill in these models, particularly the role of the initial Labrador seawater density in driving later predictable changes in the subpolar North Atlantic uprush heat content, we look at the lead regressions between the initial Labrador seawater density, as well as the Labrador seawater thickness and uprush heat content, salinity, and deep ocean density. So first we can look at this in EN4 to see whether this mechanism that was found in Steve Yeager's paper from 2020, which found a clear link between this initial Labrador seawater density and later predictable changes in the uprush heat content, whether that shows up in the observations that we have, the base observations that we have here. And so we see that initial densification in the interior Labrador Sea is associated with Labrador seawater thicknesses, which do dissipate with time but persist farther east, about at 45 degrees north, similar to the density anomalies at depth, so seen here on the right. And then this is also associated with warming in the subpolar North Atlantic. These anomalies persist, so the warming just spreads northward over time, as we'd expect. And we don't have the AMOC, but we suspect that the AMOC is strengthening here as well, leading to this warming. And so we can look at this in our high skill models. This is the regression for one of our high skill models, HAB-GEM3. And so this time we can actually include the AMOC stream function and the barotropic stream function. And so this is similar to what is found in EN4. So associated with Labrador seawater thickness anomalies, which dissipate over time, but persist in the east. And also associated with a spin-up of the subpolar gyre and a strong AMOC, which then persists throughout the simulations, and then warm water subsequently being carried northward into the eastern subpolar gyre. And this is consistent across high skill models. CESM shows the warming spreading to the western subpolar gyre as well, but then in CMCC and then as well as here, it's limited mainly to the eastern subpolar gyre. On the other hand, in the low skill model, in low skill models such as CAN-ESM5, AMOC is initially very strong, and there is some warming in the subpolar gyre, but the warming shifts southwards over time, so it doesn't persist farther north. Density anomalies and Labrador seawater thickness anomalies remain restricted to the western subpolar gyre, and then in the east, we actually have an association with negative density and Labrador seawater thickness anomalies. Other low skill models either show similar results, so F goals in BCC, or in the case of BCC, there is no link between the Labrador seawater density and subsequent changes in the uprush heat content and the AMOC. And then models in between are more all over the place. Some of them look more like low skill models. Some of them look more like high skill they're a little bit more all over the place. And so what we've determined here is that models with a high subpolar North Atlantic uprush heat content, so on the very high end of the spectrum, show stronger relationships between this initial interior Labrador seawater density and the later subpolar North Atlantic uprush heat content changes mediated via AMOC and a spin-up of the subpolar gyre, as found in Steve Yeager's paper in 2020, where he analyzed CESM1 and tried to analyze that mechanism. Whereas in low skill models here, so our lowest skill models, they either show no link between the initial Labrador seawater density and the subsequent AMOC and subpolar North Atlantic upper ocean temperature, or they show an initially strong AMOC in the case of Canny SM5, for example, which then rapidly dissipates and is not associated with a persistent warming of the subpolar North Atlantic over time. And in these models, the deep density and Labrador seawater thickness anomalies remain restricted to the western regions, and they do not show up at all in the eastern subpolar gyre or near 45 north. And so it's not clear what even drives AMOC or the subpolar North Atlantic upper ocean heat content variability in these models. Regressions, I've looked at regressions with the Erminger Iceland basin's density rather than the Labrador seawater density, and that doesn't show any link to AMOC, so it's not exactly clear what the mechanism is that drives the upper ocean heat content in the subpolar North Atlantic in these models. That's all.
Any questions? Looks like no questions. So thanks, Dylan. We'll break now and reconvene at 3:20 for a few more talks and discussion.
So we get an extra 5 minutes.
Jared?
I was just arguing for a longer break.
So,
Prognostic BGC. And then I don't know what more we discuss about it, but I feel like that's it. And then like how it seems like then this could be used as like kind of a tuning tool for prognostic BGC. Like what if we're getting negative skill as a result of long-term trends? I don't know if it's long-term trends, but it seems more likely to me.
Mm-hmm.
Then we should not have negative skill. Like what if we've got something wrong, and then you could do like PPEs to. There might be things we could already do with PPEs that exist to see what would be needed.
Yeah, I think that's a good topic for discussion.
Depends if the relevant people are here, but
Yeah, without Judith and Abby, it looks like they've gone. All right, I think we should get going and people will trickle in. So our next speaker is a double header from Nina Omani and Emily Riddle of RAL. And I'll hand it over to you.
Nina, could you share the screen? Great. So Nina and I will now present our talk of feasibility assessment of decadal forecasts for anticipating disaster impacts in the Sahel region. In addition to these results over the Sahel, at the end, Nina will give a short teaser on some results over the continental US. These are results from a pilot project that is a collaboration between NCAR and the United Nations Office for the Coordination of Humanitarian Affairs. Nina, can you change the slide? UN OCHA coordinates anticipatory action frameworks around the world, which are shown here. These frameworks operate for 2-year windows, and they help the UN respond better to disasters by predetermining meteorological triggers and responses and pre-allocating resources. Their work requires forecasts at timescales ranging from days and weeks for rapid onset hazards such as floods and cyclones, to seasons for slow onset hazards such as droughts, to years for longer term planning and resource allocation. Our collaboration focuses on the decadal timescale, exploring whether there's utility in forecasting and planning on timescales beyond a few years. Change the slide, Nina. So the focus of the project is on the Sahel, partly because studies have shown that the Sahel demonstrates large decadal variability and relatively high predictability at decadal timescales. The lower left plot here shows a time series of Sahel rainfall, averaged over the box at the top. You can note the large multi-decadal swings in precipitation in this region. The plot on the right shows multi-model hindcast skill from the WMO based on 16 decadal precipitation systems for forecast systems from around the world and showing the Sahel as a region of high skill across these models. Go ahead and change the slide, Nina. So the research questions that we're going to be addressing in this talk are related to the CESM decadal hindcasts. How well do they predict the Sahel rainfall variability at these decadal timescales? How does decadal skill vary from country to country? And then how do factors such as improvements in model physics, model resolution, model initialization, and ensemble size impact skill over the Sahel? We're going to look at how the CESM predicts changes in extreme precipitation events and whether these results are similar or different over the continental US. And now Nina will present our results.
Oh, Nina, you're muted.
Sorry. Thanks, Emily. I'm Nina Omani, and I will continue from here with the model configuration and results. So this study compares four CSM versions, each different in resolution, ensemble size, initialization, and model generation. First, there is DP CSM1 at 1 degree resolution with 40 ensemble members initialized annually. Next is DP CSM1 HR, higher resolution versions with 0.25 degree atmosphere and downgrades. This system has only 10 ensemble members and is initialized every other year. Then we have historic CSM2, an uninitialized historical large ensemble, more like historical simulation. Its skill mainly comes from external forcing. Finally, DPCSM2 is the largest generation, is the latest generation initialized annually with updated model physics. Together, these configurations allow us to make apples to apples comparisons to isolate the effects of model generations, resolution, and initialization. Forecast skill is evaluated using the anomaly correlation coefficient, or ACC. Here, ACC is calculated for the core rainy season, July through September, and for lead times of 1 to 5 years. CSM2 shows the strongest skill over Mali and Western Sahel. The improvement relative to CSM1 is consistent with expectations that updated model physics and improved circulation representations allow the model to better translate precipitation ocean signals into rainfall variability. There's also regional exceptions. Mauritania is the clear exception, showing lower skill or negative ACC in blue shades in both low and high resolution CSM1. This shows that Sahel predictability is regionally heterogeneous in older models. So here, the study zooms on Mali during the core rainy season, comparing initialized CSM2 with 20 members to uninitialized historic CSM2 resampled to 20 members. The ACC increases from about 0.6 to 0.8. This is a considerable improvement and clearly demonstrates that initialization adds a skill beyond external forcing alone. Next, this slide breaks the Mali case study into two additional apples to apples comparisons. On the left, we examine a physics upgrade moving from CSM1 to CSM2. In this case, skill over Mali during July, September increases from about 0.25 to 0.8. In the right, we examine the resolution upgrade comparing CSM1 to CSM1 HR. Increasing resolution improves ACC from roughly 0.25 to 0.43, which is a smaller gain. That suggests while higher resolution can improve sea surface temperature structures and reduce biases, it's not the dominant factor for improving regional rain forecast in the Sahel. Previous work shows that Sahel rainfall is tightly linked to Atlantic sea surface temperature gradients, and models that better represent this SST rainfall relationship are more effective at converting predictable ocean variability into skillful rainfall forecasts. We also examined the role of ensemble size, increasing the ensemble size from 20 to 40 members resulted in only small improvements in ACC. This is consistent with the previous findings that beyond a certain point, adding more ensemble members does not substantially reduce forecast uncertainty. Another important aspect is extreme rainfall, defined here as events above the 90th percentile. CSM2 captures the increasing trend in extreme rainfall with reasonable skill with an ACC of about 0.6. The forecast for 2025 to 2029 indicates wetter than average phases for the Sahel. This signal is also consistent with the consistent with the WMO multimodal ensemble, and this has direct effect on disaster planning and flood mitigation. The next slide. So this we also highlighted regional differences in forecast skills over the CONUS. CSM1 in panel B outperformed CSM2 in panel C, and high resolution in panel A across most regions except along the West Coast. West Coast precipitation is strongly influenced by Pacific SST-driven storm tracks and circulation patterns that are sensitive to ocean resolution. So high-resolution models better capture SST fronts and mesoscale variability there. Forecast skill depends, based on these results, forecast skill depends on both region and model configuration. Our results also shows that the choice of observational data set matters. When validating our results against CRU observation data set, CSM1 outperforms CSM2, introducing uncertainty into skill assessment. Is in contrast with the previous research, which shows in generally CSM2 outperforms CSM1 over the CONUS. For this reason, our future work should include multiple observational data sets to ensure more robust results. Finally, last slide. In summary, this study shows decadal prediction for the Sahel is both feasible and skillful, especially with advanced models like CSM2 that includes initialization and updated physics. These forecasts can support strategic planning for agriculture, water management, and disaster preparedness over 5-year horizons. With the Sahel expected to enter a weather phase soon, these tools are valuable. And future research will focus on understanding how temperature and relative sea surface temperature indices related to Sahel rainfall variability, aiming to identify large-scale ocean signals deriving predictability at decadal time scale. And yes, thank you for your attention, and we welcome any questions and your feedbacks.
Any questions? No questions. Thanks, Nina and Emily.
Sure, thank you.
All right, I'm up next, and I'm going to talk about this broad problem of reducing uncertainty in projections of U.S. hydroclimate, work that we're doing as part of a CPO-funded project. And I'm specifically going to introduce an analog approach that represents our first steps at tackling this problem. So the rationale here is, how can we reduce our climate projection uncertainty on regional scales where the information is really needed? And we know from prior work that internal variability is a dominant source of uncertainty in regional climate projections. So the left is a well-known figure showing uncertainty in mean surface air temperature over the British Isles, with that internal variability component dominating out to about a 30-year lead time. And more recent work by Lehner et al. has revisited that result using a larger collection of ensemble simulations and some modified methods, and has found for the same British Isles region that internal variability is even more dominant than previously thought. But we don't know what fraction of internal variability is potentially predictable and thereby potentially reducible. So that question has given rise to the field of initialized decadal prediction, where we're trying to reduce the internal variability uncertainty through initialization of the coupled Earth system. The added value from initialization is most evident by focusing on the residual after removing the force signal. And that's shown here in this set of results from Doug Smith's multi-system analysis. And I'm just going to highlight this, this left-hand plot here that shows surface temperature over the subpolar North Atlantic region. The observations are in black, showing a strong forced signal. The initialized decadal predictions in red clearly outperform the uninitialized predictions in blue, but presence of this strong trend means that the skill difference between initialized and uninitialized is very small. So it's hard to detect on the regional scale much added value of initialization. But if you remove the forced component from both observations and the decadal predictions, so we're now assuming that the blue curve is an accurate representation of the forced signal, then we're left with the residual, otherwise known as the internal variability, and then we can get a very robust quantification of the skill that we're getting in initialized decadal predictions, and it really pops out over the North Atlantic sector and into Eurasia. So this impact of initialization is evident clearly for temperature, but also precipitation, including the Sahel, as we just heard about, and atmospheric circulation fields. But one thing to note is that the impact of initialization, while quite strong in the North Atlantic is quite modest in the Pacific. So we've got good skill improvement related to Atlantic multi-decadal variability, but a generally low skill improvement for Pacific decadal variability. Although recent work has suggested that this may be due to system deficiencies rather than a fundamental predictability limit. So the aim here is to assess the potential to reduce uncertainty for future decadal hydroclimate change over CONUS by constraining potentially predictable large-scale internal modes of variability, which I'll refer to as IMOVs. The method is to analyze the CSM2 large ensemble. So we've got 100 members that span 1850 to 2100. We'll separate low frequency internal enforced variability, focusing here on annual mean fields, and then evaluate the skill of IMOV analog ensembles in a perfect model framework. So to clarify the approach here, I'm starting with a time series of regional average surface air temperature over the Pacific Northwest. And the blue line here is the 100-member lens ensemble mean, and the shading shows the range across the internal variability within that 100-member ensemble. The darker shading here is one standard deviation in the large ensemble. And then I've chosen one member from the large ensemble randomly to show you what that internal variability looks like in a given member. So there are prolonged periods where any given member can lie well outside the expected distribution of internal variability and towards the tails of the distribution. Now, I'm showing you skill scores here, which quantify how good is the large ensemble at predicting that selected member. And the skill is very high, because as you can see by eye, much of the variance here is associated with a forced signal. So we get a high correlation, a high mean square skill score, and reasonable normalized root mean square error. And then this final score is the normalized continuous rank probability score that measures basically the sharpness and accuracy of the ensemble in capturing this black line. And the point here is that the skill of an uninitialized historical ensemble at predicting evolution in a single member using the leave one out approach is high. Here's what it looks like globally for those different four metrics. We get high ACC almost globally, even more over land where this forced signal is largest. But we get the highest root mean square error over these ocean regions where these large scale modes of internal variability are most active. The normalized CRPS is pretty low by my eye. This is normalized, so it's in units of standard deviation of the target member. And over CONUS, we're seeing values of 0.3 or less. So the forced large ensemble yields widespread good skill, but can we do better? So I'm going to adopt this residual approach. So I remove the forced signal now, and I'm left with an ensemble that has no forced signal, but it still has spread. And now I can redo the skill analysis, and my correlation is now 0. I've got a mean square skill score of 0, normalized root mean square error of 1 by definition, and it turns out that my CRPS is about 0.6, and this is what it looks like spatially. So the forced large ensemble yields good skill, but low residual skill, and that, of course, is by definition. So what we're going to try to do is see if there are methods to improve that residual skill by constraining the variability of large-scale modes. And I'm going to focus on two modes here, AMV and IPO, and focus purely on the internal component. And this is what this variability looks like in the CSM2 large ensemble, 100 members. Internal variability fully developed. Each member has its own AMV and IPO. And if you regress for that chosen member what its AMV index looks like in terms of surface air temperature, then you see the well-known horseshoe pattern in the Atlantic, and the well-known IPO pattern in the Pacific. And then this is my analog method. So I've got this library of internal variability, internal decadal variability from the large ensemble, and I'm going to put that in a phase space that is represented by each of these gray dots, which is 1 point from one member's AMV and IPO. And then my target member carves out this trajectory in this phase space, and just shown you what those values are at different decades through that trajectory. And then for each point in time, I'm going to look for analogs of this target member's phase of these large-scale modes of variability. And I'm going to construct a 100-member analog ensemble whose large-scale internal variability matches that of the target member. And when I do that, I end up with what I'll call IMOV analog ensemble. So I'm able to strongly constrain just the state of these large-scale MOV indices, and I go from this gray distribution of internal variability to this yellow distribution that is clearly constraining the internal variability. And so I do this at each point in time for the target member, and basically do a giant reshuffling of the CSM2 large ensemble. And then I ask, how well does that analog ensemble reproduce Pacific Northwest temperature variability in this target member? And you can see by eye how I've reduced the uncertainty from this blue PDF to this yellow-orange PDF. And so I get higher skill scores where I want them to be higher, and lower scores where I want them to be lower. So we can say that constraining internal variability of these large-scale ocean modes then translates into reduction in uncertainty for regional climate over land. And of course, that's coming about because we're constraining the internal variability component, right? So that's what I'm showing you here. The skill scores here are from a few slides ago, and you can see that now we're getting reasonable skill scores for the internal component of variability over the Pacific Northwest. And this is what this looks like spatially. So for this particular target member, if we constrain AMV and IPO, then it makes sense that we get improved skill scores over the Atlantic and over the Pacific, but that constraint on the large scale modes has teleconnections over land. And in particular, you can see this big ACC over the Pacific Northwest. And that was the region that I focused in on. Reduction in root mean square error and a sharpening of the probability distribution. So that was for that one chosen member, but I've got 100 members, so I can redo this for each different member and then look at what's my mean skill improvement. And I should mention that these skill maps are just for the internal component only. And this is the mean skill improvement that I get across all those, across that distribution of skill scores. So we get big ability to constrain regional climate over the Pacific Northwest, which, as you might imagine, is related to constraining the IPO, but also constraint over the eastern CONUS portion that may be related to AMO. But significantly, we also get a lot of uncertainty reduction in hydroclimate. So this is showing the analog skill for precipitation and vapor pressure deficit with this big region of skill improvement over the south central US. This is the 90th percentile of that distribution. So in some members, doing this MOV analog approach is extremely effective at constraining internal variability in large regions over CONUS for quantities that matter, but some members show much less skill. So there's a wide variety of skill that we could hope to achieve in a kind of perfect model context with perfect predictability of IPO and AMO. So the summary here is that we're just demonstrating that an MOV matching analog technique could potentially significantly reduce uncertainty in regional decadal climate variability. In perfect model world, this offers some insight into decadal predictability limits with the usual caveats regarding model fidelity. So coordinates hydroclimate variability, and in particular vapor pressure deficit, exhibits potentially exploitable relationships to large-scale decadal ocean boundary conditions. So we've kind of demonstrated the proof of concept here that there's a lot of that internal variability over CONUS that's not irreducible. It's related to large-scale modes. If you could perfectly predict those, you could potentially reduce climate uncertainty. And so work is underway to extend this technique. This is not, what I've shown is not at all predictive. It's just kind of showing what you could do if you had a perfect decadal prediction system, basically. And then we need to move from perfect model to real world and look at how this works across multiple large ensembles. So big outstanding questions: what contributes to this large skill spread that I showed? And the million-dollar question: how predictable is real world internal variability? So I'll leave it there and take questions.
Claudia.
Thought I heard it.
Claudia has a, yeah.
Oh, Claudia?
Hi, I should look there, but my screen is here. Thank you, Steve. So I think you are starting to answer my question, because I was really confused. That there is no prediction going on here. You have that phase space, every point is an ensemble member and maybe a year, or what makes up the cloud of points? And then you look for the nearest neighbor of all your points, but you know where those points are. And the problem is that in the real world, you would have this mess of a spaghetti that moves around chaotically, and you wouldn't know where the next point is. Am I right, or am I wrong?
That's correct. So,
Okay.
you know, to turn this into a predictive method, we have to somehow predict where this point is going to be in phase space.
Right.
In terms of large scale modes. So we're not doing that yet, but we're doing something sort of analogous to running a large AMIP ensemble, but it's fully coupled, and we're just leveraging the CSM2 large ensemble to sort of reconstruct an AMIP ensemble, if you will, where the SST variability for IPO and AMV is as it should be.
Mm-hmm. Yeah, okay, thank you.
So in other words, you have your large ensemble, and you're saying, I know what the history is, the IPO and the AMO, and I'm picking my analogs based on which one most closely matches that.
Yeah.
Yeah.
You're not propagating those analogs forward
No.
at this point. You're
No.
just, sorry, I missed the
But you
beginning.
could, I mean,
But
like
you
with
could.
the model analogs, you would pick a point
Right.
in the run, and then you just see how it evolves in the run, and that would be your prediction.
Right. So the way,
Plot as a plot of vectors that shows you where the point is going next.
right. Right. So there are various ways that you could think about turning this into a predictive framework. You could choose analogs based on their, recent trajectory history, or you could base your analog selection on known precursors to these large scale modes, right? Which from the literature, from Dylan's talk, we might choose, Labrador Sea density as a precursor to AMV, right? So that's where this is headed. Right now, we're just asking if we could do a perfect job predicting these modes, how much could we hope to reduce uncertainty?
And there's no reason to think that if you use a mode of variability that was constrained to like one hemisphere or the other, you would see any difference, like SAM for example, rather than these interhemispheric modes.
Well, so Summer's kind of looking more into that,
Okay.
with which mode is most
Predictable or Yeah, useful.
impactful
Okay.
for our region of interest, which
Okay.
is CONUS. But if
Yeah.
if you're interested in South America, you might choose a different.
Yeah.
And then you should do the backwards problem. So both Libby Barnes has done this and we've done this, Kenya Turidi, in our group, where effectively it becomes a machine learning problem first, where you're trying to basically predict what trajectories are going to be closest to an observed trajectory. So I always call it the backwards one. If I knew what the answer was, I could go into the model, find the closest answer in the model, and then just go back and see what the initial condition looked like.
Yeah.
And you could potentially do that for different targets. So she's done that. Libby's done that for like North Atlantic sea surface temperature, I think, on like decadal timescales, and Kenya did this for ENSO. And so then that also gives you some sense of what the predictors ought to be, what variables you should pick to best constrain your models. So that might work here too, because basically Kenya was using a large ensemble to train it. So you might be able to do the same thing.
What time scales were they?
Well, he was doing ENSO, so he was pitching. He was basically, the way he would do it, the way he was doing it was he was essentially looking at 12 months, 9 months, and 6 months, I think. So it was a way of trying to pinch the trajectory in the model to kind of match an observed trajectory. So he did it in the perfect model sense. So you take, same thing, you take like one ensemble member effectively and try to find other trajectories that match. And this is this very complicated UNet that he then applied entirely in the real world. So he used it in the CSM, but with initial conditions both in the real world and made the forecast. So it's good. You wouldn't have to do it, I think, quite as complicated as his, but I think that you could do a simpler version.
His name again?
Kenya Turidi, Torite. I can send you the paper. And like I said, Libby's done a couple of these too.
I have a question about where you show the improvement of the vapor pressure deficit is actually where temperature or saturation vapor pressure plays a dominant role there. And do you actually check whether the improvement is because of saturation vapor pressure or because of humidity, which we know it has a lot of biases in the model itself?
Well, in perfect model world, there's no bias. But the answer is no. We haven't yet decomposed the drivers of this VPD signal or what the kind of key predictors are, I guess. But as I said, Summer is kind of looking more into those details than I am.
And that's like an annual signal. That's not a seasonal. Okay.
Also the region where it's like most moisture limited, right? Where it really could matter a lot if you've had rain or not as to whether there's evaporation. It's like that classic paper of the Lace experiments. That's like one of the land atmosphere coupling hotspots.
Very important region for extreme weather.
Steve, I think I'm kind of curious, like when we apply this in the real forecast, in the real world, like, how do we reconcile between this method and making the model overconfident, I guess?
I don't know what you mean by making the model more confident.
Just because we're essentially reducing the model spread in this case, right? Like considering if you already have your model bias and everything. I'm just going to think about that in my mind because, we want the model to spread enough to include the observation, in the perfect world. But in the face of model bias and, the risk of overconfidence, I don't know how do we apply this in the real world?
Well, I guess, first of all, there's a lot of complexities involved here of how you'd apply it in the real world because you have to remove a forced signal, which is very uncertain in the real world.
Right.
So you have to have the internal states of these modes to be able to kind of leverage our library from CSM2LE.
Mm-hmm.
But then as far as avoiding overconfidence, you'd have to test that out in hindcast mode and see, is that a problem?
Very promising now.
Yeah, I guess I'm wondering, like, compared to like Clara's papers about, well, that I was also involved in, the like how evaluating the model's response to ENSO, like how well do we know it in the real world, and saying there's like this huge uncertainty. It's not, yeah, there's all this other random variability that prevents you from always seeing the ENSO signal. That seems like a little contrary to that, but maybe it's just you have.
Yeah, but we're looking closely at Clara's paper with Adam, where she looks at the internal AMV teleconnection, compares it to sort of estimate of the observed internal AMV. And it's actually quite good in the model. And so Summer's looking at doing that for PDV. And so far, it looks like the model is pretty good at getting for teleconnections to decadal modes.
Yeah, I guess I believe it's good. It's more that I feel like the argument is like, if you have one member, there's all this other noise, so you don't really get to see it. But yours is kind of suggesting that's not really true, that you can kind of get skill over the land.
But it's specified though. You're specifying you're specifying the ensemble in the model. So it doesn't say what would happen if you had a different, it doesn't say anything about predicting the SST anomalies. You basically, those are a given. And you're verifying against the model itself too. So you're still in the model space. So whatever random,
I guess I would have thought the model just would have more unpredictable noise that would make this not work so well.
Right.
But it does work very well.
Well, but the beauty of the model is that
the model definitely has a lot of unpredictable noise. Even if you're pinning the IPO and AMV, you can see that.
Right.
There's still a pretty good spread here.
Yeah, that's true.
But you just get signal that is better than not doing it.
Yeah.
When you're averaging over, on decadal time scales, ENSO is the big source of noise. And your ENSO signal in the model is not as good. So there's that. So you don't have as much to average over. And B, you're averaging over what you have because you're trying to get a longer term. So you may be averaging enough that it doesn't matter as much.
Okay. So next we are going to move into discussion. I think we had thought of pulling up the discussion questions from yesterday.
Do you have it? Have it?
Yeah, I have that. So these topics are still relevant here, and I guess we'll just open it up to gather feedback from online and in the room, and then resort to these topics if no one has any new ones.
I guess I'm wondering about plans for CSM3 initialized predictions with MT or LT, or is there a kind of plan for how to go about that?
There's no plan, and you know, it's unclear to me whether, you know, that's the purview of ESPWG or, you know, just some larger, broader effort.
Yeah.
What do you think? I mean, yesterday I suggested, you know, that the first step is scoping out, kind of using our existing methods and maybe doing some case studies and seeing what delivers the most skill. I think at the end of the day, our goal is to have the most skillful system that we can. And then, you know, worry about the cost of that
Yeah.
later.
Yeah, I feel like there could be value to waiting and doing what you're suggesting, because like with your method for de-drifting now, it seems to open up a lot of doors, and we could figure out this land thing, I feel. See what's optimal. Like, do we want to run actually with satellite phenology instead of BGC? We could look at resolution impacts. We could look, I feel like there's signals to do with the QBO that we're not capturing. We could try and understand.
So you think, despite your recent paper, the high top doesn't deliver real skill improvement, we should go with a QBO enabled prediction system?
I mean, it did give a Holton Tan effect. It just was too small. So it didn't, normal skill metrics, it didn't produce actual skill. But I wonder if there's things we could do to try and see whether we could make that signal bigger. Like, what if we went a quarter degree and then that jumps out as being way bigger?
But do we really think improved resolution is going to help?
I don't know. I feel like I don't know.
I think that's a big question, and I'm not necessarily convinced it will broadly, but.
What are you running at right now?
1 degree.
While sitting in here, we missed Cecile's talk on quarter degree camp.
Oh, okay. I mean, I do wonder if, like, for the QBO case, if like capturing better wave breaking in the subtropics would like.
So horizontal resolution, you're not talking about vertical resolution.
Well, we'd need to have the high vertical resolution to get the QBO, but yeah, I'm talking, sorry, horizontal, not going higher than what we already have.
Yeah.
But I don't know. I feel like that's a whole research project to try and understand.
But you're focused on the QBO because your tropical skill is so bad, right? There's more skill coming out of the tropics still. You still have to get that right.
Why is our tropical skill so bad? I feel like we have good skill.
Subseason, well, I mean, at least when I looked at Yaga's paper, it basically seemed to say you guys have no skill coming out of the tropics on weeks 3, 4. That's pretty counter to, and that's why I would compare the
So
FFX.
you were skeptical of Kai's parameterization for QBO MJO couplings. You don't see that as like a band-aid for a prediction system to get better MJO.
Maybe, but I feel like you could also just do a statistical connection between the QBO and the MJO and predict the QBO. And
Why is your tropical skill not?
I'm not sure where, are you talking about what?
I'm talking about Yaga's. I mean, Yaga, the whole point was that thing saying, well, we're not getting any skill out of the ocean for what, lags of up to a month, 2 months. Look at how far. I mean, that's just counter to every other model.
Yeah, I thought we had, I mean, we have very high ENSO skill, right?
No, I mean, in terms of skill coming in the even in the exotropic signal.
Oh, okay.
I don't never totally understood that result.
I mean, I feel like there were some revelations about the tropical land today that I feel like is we're getting the trends associated with the BGC wrong. I feel like we had.
You just talked to me like with the BGC, they BHIS instead of the YCSM2 was worse because it was using biases with the BGCs.
Like the land was producing negative skill
Yeah.
in the coupled
Yeah,
run when
that's right.
we have BGC, and
That's
then in
right.
Abby's run,
With the,
and I'm pretty sure there's not BGC
yeah,
prognostic leaf area. It had way better skill over
Yeah.
tropical land.
yeah. Like it, yeah,
You can't use satellite phenology in a prediction
yeah.
framework with
It's-
cheating, right?
It's a climatology, so it's not time evolving. So it's, I don't think it's, I think that's what many centers actually use, right? They don't have a prognostic leaf area. So I think it's like, do we just not have leaf area being predicted, or do we predict it wrong? I feel like is the two
It might be
choices.
worth quantifying, right? It's like,
Yeah.
is this really a thing? Right? That
Yeah.
could be something, that could be like a step, a first step that you would do.
Yeah, I feel like there's very obvious steps now to understand that.
Yeah.
What is the role of the long-term trend? And then what is the role of deviations from that, and what is going wrong with the BGC?
What timescales? I mean, prediction's all about the timescale. What timescale do you care about?
I guess I'm referring specifically to what Judith was talking about, which was,
Subseasonal.
That's what she was doing S2S, I think. right?
yeah, but
Right.
your point was that the trend is the fourth signal.
Well, so there's two things. So the trend is so it's a metrics problem. And it's just that because the trend is such a large anomaly in temperature, then when you do any sort of verification, you're basically baking in the trend in your initial conditions. And it's not like your forecast is going to suddenly lose the trend, even if it doesn't have it quite right. So you have a massive improvement in skill solely because the trend exists. You don't predict it, it's just there.
Yeah.
And so that's a problem on even subseasonal timescales. You think, well, I don't care. I mean, how much does the trend change in a couple weeks? It's like there's an error, but that's not the big problem. So you need to come up with metric. I mean, we struggle with this all the time, that you have to come up with a metric which basically is not relative to essentially a fixed climatology. And if you do something relative to persistence and you run into the problem that, well, some of your scale should be persistence and you don't want to get rid of that. Yeah. So then you end up having to detrend your data and detrend your hindcasts. And then now your hindcast problem has become a trend detection problem because you got to get the trend out first in order to figure out what your underlying skill is. So that's what I was, I mean, and there's this Wolf et al. Paper talked about that was the thing I sent to her. But that's a separate issue from asking what gives you skill on weeks 3 and 3, 4, 5, 6. And I would worry more about ENSO than I would worry about getting the leaves right, to be honest.
But I think my point is that if the force signal, say in reality, is that the land surface is drying out and evaporation is reducing, and we have CLM.
You don't have to predict that over 3 weeks, though. That's what I'm saying. There's no, you don't.
I'll just let me, okay, but so that's one thing.
Yeah.
Then suppose CLM is like responding to CO2 in a way that is just producing all of these leaves in the prognostic BGC,
Right.
so that the force signal in CLM is actually an increase in evaporation. Then you're comparing those two things and you're going to get negative skill.
Yeah, but do we know that the error, if there is an error in the trend, which we're assuming,
Yeah.
do we know it's in the prognostic fully coupled, or is it in the initial condition itself? Like, apart
Yeah.
from Jerry's, showing that soil moisture over the US looked reasonable, nobody vets our land initial conditions.
I guess I'm assuming that Abby and Judith were using the same land initial conditions in there. And then they were letting the model evolve in one case with prognostic BGC and one case without. But maybe I misunderstood what they were doing.
I mean, there's an error in the trend in tropical Pacific then. You should worry about that because you get that trend shows up at week 3. You can see that in the IFS. This is also in this Wolf et al. Paper. They showed that error. And that was the whole point. What we were trying to say about trend errors is they're very fast. I mean, yeah, there's a lot of those there's a lot of those kind of errors, but that's what I'm saying, is that every time you look at an error like that, to me, I would, if I'm trying to get a subseasonal forecast right, I would worry about getting the tropics right first. I mean, it's not that the land doesn't matter, it's that that's probably a much harder problem.
But Judith was predicting, well, yeah, I don't believe that just prescribing the SSTs is gonna give you this way better scale over all the tropical forests. I feel like the bigger difference is between those two runs is gonna be the land. But we can see that. We'll be able to test it. Otherwise, we would see ENSO related patterns. We wouldn't see it mapping on to.
Right. If you care about something like, yeah, you're trying to predict, I don't know, South American rainforests, and yeah, you have to model South American rainforests, but you were talking about QBO, MJO connections, and well, we want to get the QBO right, and that's what I'm saying. That's my response is, those are all great, but if you don't get the tropics right, it's still, those are the first order effect. And so anything for MJO, that's where your predictive skill is.
Yeah.
QBO gives you something, you can have some land surface feedbacks when you get out in summer, but you have to get the basics right first, I think. That to me is the basic. I mean, I would worry more about the jet drift, right? Why does the jet go north so fast? That has a bigger impact on your teleconnection sometimes than getting anything wrong in the tropics. So you're right, you could prescribe everything in SST in the tropics, you could still have a problem in the exotropics on subseasonal timescales, and there are papers people have looked at on that, where it's just the fact that the jet is in the wrong spot makes the teleconnections too weak. So again, pretty much all the sub-X models, I think that's a problem. IFS, that's a problem. They seem to be bigger. I guess I'm just.
But don't we have very good tropical skill? I thought we did.
Yeah, and what Judith showed was prescribed SST, right? So the tropics are perfect. Apart from the land, which is what we think is kind of low-hanging fruit for starting to improve CSM3 sub-seasonal before we tackle longer timescales. Cheaper test bed. So, I think these tests that we're doing with CSM3, maybe there's an argument to switch to sub-seasonal for some of these tests.
You mean like for the tuning kind of?
Yeah.
So yeah, I feel like it seems like that would, for the land side, it might be very helpful to, if we can nail it down that what this negative skill coming in from the land is related to the prognostic BGC, then we should be able to learn from that. What do we need to do so that we at least don't have negative skill?
Right.
But maybe I think we're talking about different things. I understand your point that getting the tropics right is the biggest thing.
Yeah, no, if you have a land problem that's going to be negative skill, that's obviously,
yeah,
you have to fix that. But I mean, obviously, this should be obvious. I mean, my view is, yeah, I would focus much more on sub-seasonal, because that's when the errors are developing. You can get a lot more samples, right, for essentially the same amount of cost. If you're trying to run it seasonally, you run it, you don't even run it the first of every month. So if you run sub-seasonal, you can run multiple initializations going throughout the year.
Do you think there's something we should do quickly before things are set in stone for CSM3? Like, we could at least understand, is it a long-term trend related to BGC that's the problem? Then we could maybe inform, I don't know, choices so that that doesn't happen. Maybe it's too late at this point. Maybe it will just be better. I don't know. Anyway, it seems like there's like very clear steps to go and look at some things.
Some of these things I think are low hanging fruit for sure.
Yeah.
Yeah, I think the cheapest test bed for CSM3 is the prescribed SST S2S
Yeah.
set.
And if we could run, I guess if there are like case studies we could do where we could run it with BGC on and run it with it off and then show that there's a big problem and then perturb parameters. Or, I don't know. I saw Katie was on there earlier. Oh yeah, she's still there. I don't know. Maybe she would have thoughts on the land side for PPEs.
So Brian is only doing PPE in the atmosphere.
Yeah, but Katie and Daniel have. Abby Swan's also running a couple, well, like land atmosphere PPE ensemble, just keep perturbing parameters in the land. So we could have like, I don't know, things we could look at to see if we knew what we need to make better.
Yeah, I'm here. I have to sign off in a few minutes, but in particular for land-only calibration, we've focused on leaf area index. So it's interesting to hear this discussion about the impact of BGC versus satellite phenology. I think I missed that part of Abby's talk, but what you're saying, Isla, is that her simulations were run in SP mode? And
I think so, but we didn't know for sure, but it was an F case. So and those, if you'd used the F-HIST comp set, it would have been with satellite phenology. So yeah, we don't know for sure, but I feel like it was likely.
Okay, yeah, that's kind of surprising to me. But yeah, in any case, we've done a lot of thinking about parameters that are important to the carbon cycle and to LAI in particular.
Do you focus on LAI climatology or do you also consider trends?
So far it's been mostly mean state, but we have been wondering about how to incorporate metrics that look at trends. We focus more on the spatial variability of LAI and how to calibrate across different biomes, which is really important for the land-only state.
Okay.
Yeah, but absolutely, it would make sense to look at trends.
Yeah, and Katie, is there any land diagnostic that looks at the fidelity of the interannual variability, which is really kind of key for the prediction problem? I mean, not just trends, but
so interannual variability of what?
Like LAI over the Amazon.
yeah, soil moisture.
Yeah, I mean, I know that the ILAM package looks at mean and interannual variability across all of those land metrics. Yeah, so it's possible.
But those aren't taken into account in your PPE.
Well, taking into account how. So how we select parameters is based on sensitivity to things like mean state LAI, carbon fluxes. But we could change two things, right? We could change how we select parameters for different metrics, or we could change the metrics that we assess the spread of the PPEs on. So it doesn't have to be, looking at calibrating to spatial mean LAI. It could be calibrating to trends.
Yeah. I feel like we need to narrow it down. Trends versus not trends. BGC versus not BGC.
Yeah.
And then we would have the answer. And then maybe it's not like we actually have a problem with the way we're initializing. It's just what the model is doing.
That'd be easy.
Yeah.
Maybe.
Then it would also inform on making the model right too.
Yeah. Yeah.
Yeah, so I guess it would have been helpful to have Meg Fowler here because
Yeah.
she's probably actively working on a lot of this.
Maybe we can set up another meeting.
So you're initializing it with like Era 5, is that right? Or you do these sub-seasonal?
We usually use NCEP CFS, I think.
You initialize with the CFS?
We force the land with it.
No kidding. Well, that's interesting for picking the problem right there. But I mean,
Is that the
but
trend?
but the rest of it comes out of. I mean, the atmosphere comes out of.
Jerry, is it Jerry 55? I guess it
Well,
differs.
JRA 55 has land surface variables, which at least, I mean, we use that for a flash drought study for spring and summer, and the soil moisture matches pretty well with the atmospheric moisture flux conversion. So it does, there's at least a reasonable response that seems to be pretty consistent, and it's similar to the, I think it was the CLM we were comparing to. So why not just use the land out of the JRA, which at least is going to be consistent. It's forced by the JRA atmosphere using their land model.
Sure, we can just plonk something in the land model.
No, but I mean, if you're talking about initializing it,
Yeah.
or do you have to worry about spin up? Or I mean, they've got some sort of vertical structure as far as that goes, but yeah, I don't know.
But I think CSM2S2S is initialized with the CFS2 as well, the atmosphere.
Okay.
So the atmosphere initialized with the CFS2, and the land is spin up with CFS2. Yeah, and I did a comparison between CFSV2 and ERA5. They're quite different.
Yeah, I know.
Like the land or the
just the
sphere being
atmosphere. You
Well,
look
the
at
ocean,
surface
geez, there's
temperature.
that whole chunk. You can't go before 99 with the CFS because it's something that they've never really explained totally as to what went wrong. But yeah, there's a reason they started 99.
But with the SMILE run, we're using this offline forced by trending, right?
Yeah, so we do different things for S2S and SMILE. So SMILE, we're using JRA 55 to initialize the atmosphere, and JRA 55 to force the land initial state.
Would that be worse than using, would that really be worse than using CFS?
Well, the good news is you're staying in the CLM world, so you don't have to worry about another, like I always said, sticking in another land scheme with different parameters and things like that. You're just taking the CLM, forcing it, hoping you get something close to the observer, which actually wasn't that bad for the things we looked at, which I was surprised at actually. And then you just stick that back in the model and you go from there. But the S2S is a little bit different.
Yeah.
I mean, that's, then, I mentioned this to Kevin yesterday, but, you could try using replay. And they do that at NASA, and we're doing that now, where you basically you essentially, you initialize your model with whatever 5, but you nudge a set of variables basically back, and the idea is you're trying to get an initial state, which is essentially the era. It's like an Era 5, but it's closer to the model space, so you're trying to reduce the initialization shock. And then that's also more consistent. Now, I don't know what they do with soil moisture, but I'm sure they spend time on both NASA and us. We have people been worried about that. So.
Yeah, I think we need a more sophisticated initialization methodology. We talked about that yesterday, and that's kind of looking further ahead towards a production CSM3 prediction system. But
I mean, in the long run, you might want your own DA, but this would be a good bridge. You could do this, probably set something up like this a lot quicker and cheaper. And it would give you some sense of whether improving the initial conditions, if it does help, which I would imagine probably would, then it gives you more justification to say, okay, well, maybe we have to kind of go all in on this.
how does replay differ from just atmospheric nudging?
Well, so if you start with Era 5, you have more of an initialization shock. So the idea is you're trying to reduce the initialization shock. You could think of it as a spin up of the whole initialization, I suppose. But the idea is you're trying to use the nudging just to selected variables and letting the rest of the model kind of be more consistent with those nudge variables.
But I think you could just continually nudge as opposed to,
Well, no, you're not this isn't, I mean, they do nudging experiments too, but this is just for the initialization.
but I mean to
They
get,
use the same, so the thing is they have this replay. The reason why they did this is because they had this replay set up to do replay experiments, and then they said, oh, well, we could use this replay, which was a kind of a constant nudging through the entire run to basically see. So there are some papers where they were like, say, well, you nudge the tropics and you say, if we could nudge the tropics all the way through and have something like a perfect tropics, that's the whole atmosphere. How much of an improvement would we get in the extratropical precipitation? So Juliana Diaz and a couple other people, they were doing that sort of work. But with that tool, they basically said, well, we can use that also just to generate initial conditions for every whatever 6-hour forecast that we're running.
I guess what I was meaning is we can just continually nudge as opposed to run a forecast, go back.
No, yeah, that's what I'm saying. It's not like
We
that.
can't do that.
No, I mean, you can do anything you want, I suppose, but I'm just saying that's not what the idea is just to get a kind of a consistent initial condition.
Yeah.
Just one more note on this visualization thing. Part of our project we're doing with Ruby's group is to look at, they're doing this so-called weakly coupled data simulation for land, and they've tried to institute in the ocean as well. So we were going to compare what their initial states look like to ours, that we're just using this offline forcing just to see what soil moisture looks like in the two different methods. So that's another little element to this. I'm still a little unclear how their weakly coupled data simulation system actually works, but we're going to learn more about it as we get more into this project, hopefully.
When you say weakly coupled, you mean
Well,
not strong, not like.
yeah, they're using
weak and-
GLDAS reanalysis product for soil moisture to multi-layer.
Okay.
And they're somehow sticking that into the E3SM.
Okay.
And one of the Chinese models too. But how they've got this 1 month window and then they nudge it back somehow. And I don't know, I don't really understand all that, how it actually works. And some of these areas are producing kind of odd results. We're going to get more into that. I think figure this out. But I mean, just this first look that we did at what ours looks like compared to this, one of these observed products, isn't that bad. So that's at least encouraging for these time periods.
Weakly coupled normally just simply means that you're doing DA in the components in a coupled system. That's the definition of weakly coupled.
Okay.
It sounds like it's half-assed and weakly coupled.
Define weekly, right?
Yeah.
I think they're two different things.
That's what I didn't understand. I didn't
Weakly coupled
understand.
is just a standard.
Okay.
So it means that you run a coupled system and you do DA into the component.
Okay, gotcha.
Fully coupled, people don't really know how to do, but that's where you try and take variables across the different ones in the DA itself.
Uh-huh.
So you sort of look at the atmosphere and the ocean or the atmosphere and the land, and somehow you consider all of those observations together. And that doesn't, I don't know that many people or anyone's quite doing that yet.
Okay.
Yeah, because you run into the time scale issue.
So in the midst of developing algorithms to do that. It looks like there's a way forward in Dart to do that.
Right.
Without any changes, but.
Yeah.
Right, it's basically letting observations of one component affect model variables in another.
Yeah.
component.
Okay.
That's fully coupled then, right?
Right.
And weekly just not doing that bit.
Okay.
You're still doing in principle, you're still doing a full DA of each of the components, just in the coupled system independently.
Okay. Oh, okay. Really interesting.
So I don't know if that's relevant, but I want to add one point to the initialization because I've been using ModAnalog to predict month-to-month vapor pressure deficit. And long story short is that when we include soil moisture, it actually degrades the month-to-month forecast scale. So we dive down into that, figure out, okay, Spear has very bad, the initial spread for soil moisture is very big, but we don't have actually very good ModAnalog for soil moisture. It introduced a lot of unnecessary initial spread, so it degrades the VPT prediction. So I think you can actually contribute to that initialization bubble problem there.
I think Abby is planning to run some CSM to initialize with the ERA5, right? Is that what they're trying to do?
I think she said that, yeah.
Right. Oh, yeah,
Because
that's
that's what
right.
they're using for MPass, right?
Right. So at least that's something we can look into.
Her talk,
Yeah,
she did the work.
I felt like from her talk, it wasn't obvious to me that MPass is really better.
Right. They're very
Especially when you don't have
explaining.
the BGC on.
I know. It was marginal. I mean, everything was a little bit marginal, except CSM just looked super bad.
Because, yeah, which I feel like is not because,
Yeah,
it's because of one particular thing, because we have a process that is not in the other model.
let's pick that fruit and put that to bed.
Yeah. But we have seasonal prediction, smile that are initialized from ERA5 now that can be, I mean, it's not the same thing, but we can compare that with the GRA55 ones.
Right.
I think we've seen a big difference, but
Have you looked at all?
no, just the NAO.
What's the ocean under the MPass run that you're talking about?
Observations.
Prescribed.
No, they don't have an active ocean.
So it's just fixed, or they're just doing it as a hind. It's just a fixed ocean.
Well, just prescribed SST.
Time varying. So I feel, yeah. I think it's unfair, best. We have all these other processes that are maybe going wrong.
Yeah.
So it's the observed SSTs.
I guess it's less about the SSTs. It's just that I think like the prescribed SST run looked pretty good compared to MPass, but I don't think that's because we're getting something wrong in the SSTs. I think it's because it was using satellite phonology.
Right.
But we should get to the bottom of it.
See, you were looking at the big, enormous topical errors, and I was staring at the much smaller, but at least in a NOAA perspective, more important topical errors.
Yeah.
Justice for CSM.
Sticking up for your model. Okay.
Are you working with them on that, or how do we coordinate?
I mean, they're all part of the SPAD group.
Yeah.
But I've missed the last few meetings, so
too.
I think there's some lack of crosstalk as far as I can tell.
I think
There's different working groups, right? There's a lot of, I mean, I'm not sure which working group this fits into for the SPAT working. I mean, like, you know, seems like I'm always getting invites to different meetings,
Yeah.
but I don't, yeah. I'm not sure. Like if there's a grand plan,
Right.
coordination, which probably should be.
Well, that's why I wish Meg was here. I think she would know.
Yeah.
There's one on, there's a meeting on Friday.
For extremes?
S2S predictability.
S2S. This Friday.
Yeah.
Is one test you can run to just use the MPass DICOR, but everything else the same? Keep the CAM physics and everything like that.
Oh, that's what I did.
You did that already.
It's kind of the CIMA framework, right?
Yeah, I don't know. I think you can run the MPass DICOR, yeah, within the.
Yeah. So, but I only did case studies for 2 extreme events. I didn't really run that long term and evaluate the performance and skills. Very poorly. In case you're wondering. Yeah. But I guess we can use that to test the hypothesis we had with the CLM land and MPass DICOR.
Yeah.
Right. We degrade MPass skills.
Yeah, let's give MPass the prognostic BGC.
Yes, we can actually do that. That would be another cross validation for the experiment.
But are they running the MPass physics package with the MPass?
I think so.
So I'm just talking about switching to DICOR. So it won't be, it won't answer that question because it's a gap in between. I don't think it quite gets you there, but it's, I suppose one of the reasons for this is just that, with NOAA announcing that they're going to use MPass across timescales, GFDL at some point, or whoever's doing the seasonal prediction in NOAA, is going to be working out how to do it. And they'll be running with the MOMA Ocean and they'll be using the MPass DICOR with whatever physics they think they want. There's another player in that space now.
GFDL's not really doing seasonal prediction anymore.
Who's doing it then?
No, they're running their model 4 times a year now.
Right.
Because Tom Delworth kind of threw a hissy fit, but now he's retiring, so I don't know what's going to happen.
Well, I think now we'll have a job of doing seasonal prediction somewhere within their organisation, and they made this headline statement that everything's going to be.
No, the Canadian model is the best seasonal forecast right now. Well, or the European model. CS5 is better than.
It's not about what's good; it's about what's tactical for our organisation.
No, but I think that's a real thing, though. Is that I'm saying facetiously, but it's like if you look at the United States and you ask, so who's doing seasonal prediction? The answer is there's nobody really totally responsible for doing seasonal prediction. In terms of running the model, there's an organization which is supposed to issue seasonal forecasts. That's Climate Prediction Center, which is getting swallowed up by Weather Prediction Center, so it won't be its own organization. And they rely on an average of a bunch of models that they have no control over. 2 Canadian models, CFS2, which, as I like to say, is old enough to vote, and a couple of models that Ben Kurtman runs that are your old cast-off models, and the Spear, which they're only going to be running 4 times a year.
Sounds like an opportunity.
So how does
So there's a big. I still think.
How does MPass compare to CAM7?
You guys are just passing up.
So Brian did a test for me this week on just a 2-year plan, fixed SST plan and running about the same basically. It was like a less than 1% slower.
That was the DICOR with CAM physics, or that was
running the same grid. Sorry, say that again.
MPass with MPass physics, or
So that was the MPass DICOR within the CAM framework basically. So I said take the development. I asked him to do a run of the development version of CSM3 now and swap the DICORs and look at the performance in terms of computation, and it's got the same performance. So it was like the latest run on the development at this CSM3. So we need a longer run to look at results from it. But
yeah,
it's entirely the same. It's entirely performant.
Analogous resolution.
With the same, yeah. There's some complications around how they do physics across different things, but yeah, essentially it was pretty much a 1 degree run and a 1 degree run. And he's putting a pull request in to get the grid available, so it should be straightforward to do a different kind of run with if you can do it with the stuff.
Yeah, so maybe we should attend the next SPAT, S2S, and propose
I
it
can
if
only
it
join the
hasn't
first
already
half
been
hour.
proposed. In a way, you're wrapping up the SEMA stuff, right?
Right.
Would it be easy to run a full S2S set if you have the compute?
Yes, yeah. I think the hardest part, because Patrick has done a great job of setting up the workflow, but we still need a lot of time to generate all the initial files. I don't know why it takes so long, because a lot of the SEMA grid is not the most straightforward thing to work with. So the generalization of those initial files takes some time. But once those are ready, I think it shouldn't be too hard to run the whole set.
And that was the equivalent to CSM2 S2S, right? But with MPass DICOR.
With MPass DICOR, right?
But you don't have a coupled ocean, do you?
Oh, no, yeah.
That would
we
be
don't
the
have
prescribed SST
Yeah.
So not
framework.
entirely S2S. It's like what they've done. I mean, EMC, they've run the DEFs with observed SST, and then I think they started doing some sort of thing where they did like a relaxation and. But I mean, you can't, if you're using observed SST, it's not a forecast.
Why can't we just run a couple? I feel like we can, right? We're just switching out the dicor.
I
So
don't know.
that's what I asked Brian to do.
Yeah.
I don't think you need to use a CalCIMA framework right now.
I mean, if you think you're doing a good job predicting the SSTs and the, whatever the CSM2 version, why don't you just put in those SSTs instead of the observed? At least that way you're putting in something that's predicted. And for what it's worth, you're putting in the same SSTs, which is a better comparison than putting in the observed SSTs where somebody can say, well, you got it right because you put the observed SSTs in. That'd be more realistic S2S kind of timecast. So.
Right.
I feel like we could just switch in the dicor and do a couple in the same way. Then we would.
You should get clean comparisons of the dicor
Yeah.
from the two rows.
So it could screw up the ENSO forecast. And
Yeah, you'd have to retune the whole model.
no, but you don't have to retune because you're initializing.
Well, it'll drift pretty quick though.
Yeah, so does our current one.
Well, yeah, in ways that you have no idea. I mean, yeah, you're right. I guess everything drifts, but
Lead dependent climatology.
yeah. Well, I guess, I mean, I guess we would argue that you should do that so that you can see how to fix this new coupled Frankenstein that you've made.
Yeah. Yeah. I mean, yeah, exploring the drift would also be interesting.
Yeah.
But then if we just swap out the dicor, develop a whole thing for initializing it, right? Because Brian is only testing the uninitialized ones.
Yeah.
Right. Yeah, I don't know how much work that would require.
Is it like the generation of the initial conditions or which side of it is? Because they've already been running initializing impasse, right?
Right. But I mean, in the CSM3 framework.
This is why I would do the replay.
I don't know. Yeah. Maybe it's not that complicated. I'm trying to remember why, like in the CIMA project, why it is so hard to add in an interactive ocean. Like you would think.
But that was in CIMA, right? This would just be in CSM3.
Right.
And switching out the dicor. Basically just changing, when you create the comp set, change the resolution, but then of course you need the initial conditions as well that are on that grid, but.
Right. But CIMA is basically, I feel like, is the CSM3 with MPass dicor. At least the case studies that we ran, right? We're trying to use the HOCAM coupled to CLM, like an F comp set, but with MPass dicor.
Okay. So CIMA has mom in there.
No.
Oh, so I feel like maybe the problem. I don't know.
Yeah. Yeah, I guess it's not completely the same.
Yeah, I'm not sure. Maybe there's more complications.
Right.
Than I'm thinking.
We can figure out which way is easier to implement.
Talk to Meg.
What?
Talk to Meg.
Yeah.
I'm afraid I have to leave. So, but it was a good discussion. Thanks, everyone. Thanks, everyone online. And we should have thanked everyone for their talks.
There's so many things.